Now we want to think about how do we draw bolts and threaded holes and other examples of threaded stuff. A screw thread, to be precise, is a shape with a uniform shape like this 60-degree point that goes along the axis of a cylinder, a bolt or a hole, in the form of a helix. So it's not a spiral, it's a helix, and it's turning around and around this axis. Now some words about threads. The outside, the biggest part of the pointy stuff is called the major diameter. And so this is a bolt. Down at the bottom you see a view through a hole. It's still, the bigger part is the major diameter. The smaller part is the minor diameter, and here you see it down at the bottom. The distance from one point to the next point is called the pitch. Could be from one valley to the next valley, or from one peak to the next peak. It's from one place to the same place on the next thread. That is the pitch. And we don't usually have to describe that, but what we do have to describe is threads per inch. And here's how that works. Imagine you put a scale or a ruler next to your threaded fastener, and you look at how many pitches, how many pointy things are there in the space of 1 inch. In the case of this picture that we're looking at, these are really big threads, and there are, count them, 1, 2, 3, 4 spaces, 4 pitches. So this thing has 4 threads per inch. There are all different shapes that threads could take. You might recognize the knuckle thread. If we were in person, I would ask you if you could think about where that was in your house. And you might say, oh yeah, light bulb. Or looking at the Acme thread, if I asked you about that, you might say, oh yeah, a screw jack for changing a tire. But this one that I have circled, the Unified National thread, is the one that we use for all our screws and bolts and nuts. And it's called Unified National because during World War II, Britain, Canada, and the United States decided to unify on how they made their thread shapes so that they would be able to trade parts with each other and the bolts would still fit. So there's a standard shape that the Unified National thread takes. It's a 60-degree angle in there. Machinery's Handbook can give you the data if you'd like to look it up. And there are two classes, two sizes. Most bolts are Unified National Course, and we write UNC. That stands for Unified National Course. A few cases you need more threads per inch than that. And you might think about places where you need a strong bolt, like lug bolts holding a wheel on a car, for example. Those are Unified National Fine. Fine threads have more threads per inch. But most of our bolts are UNC, Unified National Course. Now, when you, let's say, dimension your threads, you don't really dimension the threads. All you have to do is point at them with a leader and write this note. So here's the beginning of a note, and here's how it begins. It starts with the size of thread. So this thing, this bolt here, started out with a 3/4 inch diameter round thing. So there's the size of the round thing. Then dash, then number of threads per inch. Then a space, then the series, whether it's Unified National Course or Unified National Fine. Continuing on, there's another thing you have to add. You know how ASME's dimensioning rules say every dimension shall have a tolerance. Well, here's how you put the tolerance on this thread callout. It turns out that ASME has 3 classes of fit, from loose and not very precise to ordinary to close tolerance and most precise. 1, 2, and 3. If you have an ordinary bolt, like you probably use in your shop or you get from your parts house, that will be probably a class 2. So you'll say 3/4 10 space UNC, should be no space, -2 for the class of fit. And then, this is ridiculous, but you have to make an A or a B to tell them whether it's external or internal threads. I have never figured out why they thought that was necessary, but it is. So A stands for external threads. If you're pointing at a bolt, you have to say size -threads per inch, space, UNC-2A, A for external threads. And the way I remember that is I picture a whole bunch of capital A letters next to each other, A, and I think, oh, those kind of look like pointy threads. The threads we just looked at had a decimal size. This example has a fraction size. Either one is okay. Both of them are acceptable. So it's whichever your workplace prefers that you do. Now, how do you draw these things? I'll start at the bottom and work up towards the top. Detailed thread is the one that looks realistic. It also takes a long time to draw. And if you were drawing that at work, your boss might look over your shoulder and say, "Why are you spending all that time just drawing threads?" And you would say, "Oh, yeah, sorry." You would do this if you were making illustrations for a parts book, maybe, or a user's manual. Schematic threads, drafters used to do these years ago, but they don't do them anymore. So forget those two. How you draw threads, how all drafters draw threads nowadays, is a method called Simplified. And to make a simplified thread, you simply use hidden lines to represent the threads. You don't show pointy things at all, you just draw a hidden line. And you don't draw them to scale, because if you did, the hidden line would be too close to the edge and they'd all blur together. So what you do is you draw that hidden line about 1/16 of an inch away from the edge of the bolt or the edge of the hole. To help you think about that, I've stuck our first slide back in here. So if you were looking at the end view of a bolt, you would see the peaks of the threads. You would not see the valleys, would you? So the valleys, backing up, the valleys would be represented by hidden lines because you don't see those. If you're looking straight on into a hole, however, in a hole, you're going to see those minor diameter peaks that extend down into the hole, and you will not see the larger major diameter thing. So for a hole, you show the smaller diameter as a solid line, and then the part that you would not see as a hidden line. So there's a simplified thread. Here's a table that suggests appropriate spacing when you're drawing fasteners. We're drawing something where we're going to use a 1/16 inch spacing from the outside of our bolt to where the hidden line is. If you were drawing a real small one, like a 1/4 inch bolt, you might want to offset that hidden line only a 32nd of an inch. So we're going to offset our lines a 1/16 of an inch when printed. Here is what an internal thread looks like. And if you're not threading all the way through the part, if you're just making, this is called a blind hole, where you go only part way through, here is the standard way of representing those threads. Notice how there's a small diameter that goes all the way down, and then a bigger one that stops, and that is the effective thread depth, and that's caused because a drill or a tap does not have 100% good threads all the way down. They kind of taper off. So we represent that with this more clean looking stop to the lines here. And at the bottom of our hole, we draw that as a 30-degree angle. We're not going to draw a threaded hole this term, but I just want you to be aware of them. Okay, so external threads, one more time. This is what we're going to draw. External threads, you'll offset a 1/16 of an inch in to locate your hidden line. In other words, 0.063 of an inch. Now, if you pick up a bolt, you will notice that the end of the bolt has been chamfered. And that's because if they didn't chamfer the end, one, there'd be a razor-sharp edge that would cut people easily, and two, you wouldn't be able to get the bolt into the hole. So they're always chamfered, and what you draw as a drafter is wherever you drew your hidden line for your threads, you make your chamfer that size. So if you offset a 1/16 of an inch to the hidden line, then your chamfer will be a 1/16 of an inch. But you don't dimension it. You don't call it out. You just draw it. So here's the part we are going to draw. This pump pivot. It's got a weird looking handle thing on it, and then it has a threaded rod sticking out from the block. Our book put an overall dimension here. Some shops find that helpful if they want to know how much total material do they want. But we have to make, if you put it on there at all, you have to make it a reference, because we never dimension to the round end of thing. That we cannot measure that effectively. So that would just be a reference if you include it, and you're welcome to omit it. Notice that one hole has a tolerance on it that's different from our title block tolerance. That means you will need your standard dimension style plus a second dimension style for doing the hole. And you will need to locate this rod onto this block. And so there are two ways you could do that. You could have a top view and a front view and give a locating dimension in each one. Or what I think I would do a front view and a side view and just locate that shaft in the side view or the end view. I think that's cleaner looking, but up to you. And notice you do need to dimension in both directions, X and Y. Then you'll offset a 1/16 of an inch to make your hidden lines. You'll chamfer the end of your thread, and you'll use a leader with this note in it to call out the threads. So this is a 1/2 inch Unified National Course thread. Oh, look at that. It's a real loose class of fit. It's a 1A for external. And this is a weird way of pointing at the thing because it's an isometric view. You will just point at your simplified thread with a leader at an angle of 15 to 75 degrees, either off to the right or off to the left. And here's a dimension showing this is how far your threads should extend. And that means that's where this vertical line will stop.